are drawn according to P of xn tilde, P of yn tilde. And off to the side we mean, i.e., xi, yi tilde are drawn according to P of x tilde, P of y tilde, and their IID. So, if they have the right joint distribution, they'll be typical with high probability, and there aren't very many of them. But if they have the right marginals, but are otherwise independent, the probability they look like they're, as if they're dependent, is, if that, then probability that x super n tilde, y super n tilde is typical is exponentially small. In fact, it's less than 2 to the minus n I of xy, the mutual information between x and y, minus 3 epsilon. So that's very important. I have the tree rings in Palo Alto indicating wet years and dry years. And I have tree rings, this is 100 years ago for old trees. And I have tree rings in San Francisco for wet and dry years. And I wonder what year is the base year for both. I want to get them in time sync with each other. I just cut down the tree. I don't know how old it is. So I look at the tree rings, and when they're mismatched, it looks independent. When the time is just right, they look to have the joint distribution. And the weather in San Francisco and Palo Alto is very similar. So the probability that I mistake the time for the tree rings is going to be 2 to the minus ni, the mutual information between the weather in Palo Alto and San Francisco. It's exponentially small. In other words, I'll say, you know, these tree rings look typical, these tree rings look typical, but they really don't look like they were done in the same year. They don't look jointly typical. So if they're independently drawn, then the probability that they look as if they're dependent is 2 to the minus ni, and that's of course going to be crucial for our sending information over a channel, because we have this code word causes that y, cause and effect, joint distribution, and some other randomly chosen code word will not be confused as the cause of this y with probability greater than 2 to the minus ni. Therefore, we can choose roughly 2 to the ni of them before we get any confusion. Well, we'll make that specific. Ooh. By the way, This number 3 is the heart, not only of channel capacity, but Slepian Wolf, multiple access channel, broadcast channel, a number of things in the future. And we actually get the following picture from joint typicality. Here's XN, and here's YN. These are sequences. And XI, YI, IID, according to P of XY. Now these are the 2 to the n h of x. Now I drop all epsilons for this sketch. 2 to the n h of x typical x's. The rest are garbage. They have total probability nearly 0. Similarly, I have 2 to the n h of y typical y's. So how many XY pairs do I have that are individually typical? Well, that's 2 to the n h of x, 2 to the n h of y. That's the number of entries here. But how many of them are jointly typical? If this theorem is true, they're 2 to the n h of xy. So let me put down a dot whenever a pair is jointly typical. For the BSC example, these are all typical, these are all typical, and we put down a dot whenever x and y are within a distance np of each other. And how many of these are there? 2 to the n h of xy. What proportion of these, this is the total number of entries, and this is the number that are jointly typical. What proportion are jointly typical? Well, that's 2 to the n h of xy, the number that are, divided by the number of entries. And that's equal to 2 to the minus n I of xy. So the proportion of jointly typicals is 2 to the minus ni. By the techniques that we'll use to prove this more modest result here, we can prove that they're 2 to the n h of y given x conditionally typical y's for each x. They're 2 to the n h of x given y conditionally typical x's for each y. The total number is 2 to the n h of x comma y. The probability that two independently drawn x sequence, y sequence are independently drawn, the probability they're jointly typical is 2 to the minus ni. So you could see how useful this is. Not only is it useful, it says essentially all joint distributions are the same, as long as they have the same h of x, h of y, and h of x comma y. They have a bipartite graph structure such that for each of the x's, they're 2 to the n h of y given x here, and for each of the y's, they're 2 to the n h of x given y, conditionally typical x's and all the books balance. All right, now, I do have a warning. Not once you've specified, you say, oh, look, all the nodes here have the same degree. That's that. All the nodes here, for the y nodes, have the same degree. It's this. And it's a bipartite graph. That actually does not. There are a number of bipartite graphs that are distinct, that have the same degree structure. Now, we only need the first degree structure, which is to say this relationship. But if we went bounce, 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 is X typical with a Y that is typical with this other X, then there actually is a distinction. But all we need is the fact that there are just three numbers here that tell us what this graph looks like sufficiently so that we can do what we want. Okay, let's prove some things. Gee, we played cards for too long, I think. Okay. All right, let's prove it, and then prove the theorem. All right. All right, proof of AEP. Joint AEP. All right. A. To prove one, we use the law of large numbers 3 times. Minus 1 over n log p of xn is the sum of log p of xi. So this goes to its expected value minus log p of x, which is equal to h of x. Okay? So, sequence xn drawn IID according to p of x will be epsilon typical with extremely high probability for large n. And so we similarly have minus 1 over n log p yn goes to h of y, its expected value, and minus 1 over n log p of xn yn. Remember, these are random now, but they're IID drawn according to p of xy, and so this converges to its expected value, which is h of xy. So we have now proved item number 1. Number 2, show a less than 2 to the n h plus epsilon. All right, proof. 1 is equal to the sum of the probability masters for all sequences. Xn in Xn, Yn in the alphabet Y. Now that's certainly greater than if we sum over the subset. So this is A epsilon super n of P of Xn Yn. Okay? But